it on time. Okay, so thanks everybody for coming. This is the third lecture in the series. Previous lectures, we did some kind of analytic introduction to CFT and some motivations. Today is kind of the main lecture in which we're actually going to introduce the Conformal Bootstrap and even give a demonstration of how to use it using freely accessible software. Okay, so let's go over some basics which we discussed in previous lectures. So the main thing we had was the 4-point function of 4 identical scalars. So I will denote a scalar by 5. There are 4 of them, they're identical, but they are agreed at 4 different points. And so as we discussed in previous lectures, using conformal symmetry, you can factor out this x dependence and then write the block expansion in terms of what are called OP coefficients. So what the lambdas are, you have them squared, as we discussed in previous lectures, and you have these conformal blocks, which are completely fixed by conformal symmetry in terms of these 2 variables called u and v, which are various combinations of the x's. So this is the main quantity we are interested in, which we are going to bootstrap. And so let's list some properties about it. So first of all, the operators in O that appear here are all the operators that appear in the OPE of these 2 phi's, which you write as such. So remember we discussed the OP in the previous lecture, and so the kind of operators that can appear here, for instance, would be fixed by symmetry. So for instance, like say this phi was charged under Z2, if it was Z2 odd, then you would only have Z2 even guys appearing in this 4-point function expansion. Also, a certain operator we know must appear, at least for a local CFT, is the stress tensor. So for instance, we're always going to have an operator which will have dimension b in spin 2, at least for a local CFT. So other properties we know about this is that all these operators, they have to obey what are called unitarity bounds. So for an operator of dimension delta and spin L, so in general, the scaling dimension has to be greater than or equal to d minus 2 plus L. This is when L is greater than 0. And when d must be greater than or equal to d minus 2 over 2 when L equals 0. So these are unitarity bounds. This is another important thing. Also, we can always choose a basis of our operators, at least in this context, such that these OP coefficients are real, which implies that the OP coefficient squared is possible. So that's another important fact. And we also normalize the identity operator OP coefficient to be 1, which is just a normalization of operators. Another fact we learned from previous lectures is that the blocks themselves, which are completely fixed by conformal symmetry, so when written in terms of these r and eta variables, which are related to u and v as discussed before, they take the form 4r to the delta, and then we have this expansion in r, and then here we write the eta dependence in this abstract way, and then the dependence on delta is in terms of these poles. So just to go over the way these blocks look, so the r dependence is a simple polynomial times this exponential dependence in terms of delta. And then you have the eta dependence will just be various polynomials of eta, which different for each spin. And then for each m and n, you're going to have different poles and delta that appear. And so that is the structure of the blocks. And all of this can be computed recursively, as we discussed in the previous lecture. Lastly, and most importantly, and as we discussed in the very first lecture, this 4-point function satisfies things called crossing relations, which has to do with the fact that you could rearrange the operators on the left-hand side. And so one crossing equation is written as such. The other crossing equation is written like this. And so this guy, as we discussed in the previous lecture, is a bit trivial in the sense that it basically just requires, in the context of this 4-point function, that these L's be even. And so another way of saying it is that you kind of satisfy it term by term. And so this guy is not so interesting. It's this guy, which is an interesting guy, because this is the cross equation, which is going to non-trivially relate all the CFT data to some rewriting of the 4-point function with related CFT data. And so that's the guy which, is the power of the conformal bootstrap. And so we're going to use that crossing equation to derive algorithms and then show how to use them in this slide. And so the first thing we're going to do is let's just rewrite this 4-point function as follows. Can I use this board as well?
Yeah, I can
Okay.
move the camera.
So we'll rewrite this 4-point function in a way which will make things a bit simpler. So let's rewrite that 4-point function after applying crossing, i.e. the boxed equation, as such. So as usual, you're going to have a sum over the various operators with their OP coefficients. But then we're going to write it in terms of what we call this crossing function f. So it depends on delta phi as well as each delta L. And the statement of the crossing equation in the box is that this thing equals 0, where we define this f delta phi delta L to be b to the delta phi g delta L uv minus u to the delta phi g delta L v u. So all we've done is rewrite the 4-point function equation with the crossing equation boxed and introduce this new notation, just that it takes this very succinct form. So it's like this is kind of the dynamical information we want to compute, this lambda and delta, and then this is the kinematic quantity, which is what you call a cross flow for each delta and L. Okay, so now using this equation, let's write down some algorithms. So hopefully you've seen here. Let's write down some algorithms which will allow us to bound the lambda and delta, which is the stuff we care about. So the first one will be the scaling dimension algorithm. Okay, so there's two steps of this algorithm. We're writing this algorithm in terms of function of alpha, which acts on this equation. So this is a function which will act in principle on u and v in this equation. So the first step is that we normalize alpha such that alpha acting on the f for the identity operator, which is spin 0 and dimension 0, is 1. Okay, so that's our choice of normalization for alpha. Then we assume that the scaling dimensions delta L for all spin L operators except for the identity operator will obey delta L greater than or equal to some bound, which we denote by delta LB, where we can choose what we want this bound to be. So for instance, one choice would be the unitarity bound, which is written on the board over there. That's kind of a minimal choice, but in principle, we could assume a stricter bound for that. Third, we then search for an alpha that satisfies alpha acting on the f's of all these operators except for the identity are greater than or equal to 0. And if such an alpha exists, so if this alpha exists, then alpha acting on the sum of all these operators so then this thing will then be greater than 0. And so why is this greater than 0? Well, it's because this thing is positive, as we discussed earlier, and because this thing is positive, and because this thing is normalized to 1, thus this whole thing must now be strictly positive. But this is a contradiction, because this contradicts the fact of alpha acting on the crossing equation itself. Because when alpha acts on this, it says that this thing is 0. So if this thing is not 0, that's a contradiction. And so that would imply that our assumption in step 2 must be false. And so this is how you can then carve out some kind of upper bound. So for instance, what you could do is you could let these delta b's just be the unitarity value for every spin, except for spin 0. And then for spin 0, you could assume that the delta b is some value. And then if it's big enough, you're going to start getting this contradiction. So that's going to tell you that point is disallowed. And then if it's small enough, then you don't get a contradiction, which means in principle it can be allowed. And so this would carve out some space. So you can imagine some kind of plot where like as you vary delta phi, which enters explicitly in this expression, you'll be bounding this delta V0, and you can imagine some kind of upper bound like this. So then this would be the allowed region, and this would be the disallowed region. And so that's how you would do that using this algorithm. But so far, this would only allow you to get an upper bound. So without further assumptions, in general, with the bootstrap, you can only get upper bounds on the scaling dimensions. If you want to get both upper and lower bounds, then you have to make a further assumption. So in the bootstrap language, it's called a gap assumption. It's completely unrelated to the way gap is usually used in condensed matter literature, so don't be confused by that.
And you write a little bigger. The resolution of the camera is not optimal.
Okay, so we can also add what's called a gap assumption, which is that alpha acting on one of our f's for a specific delta I and Li. So I'm just using I to denote a specific one of these guys. That this thing be positive for a certain delta I, Li, which is smaller than our assumed bound for that Li. So in the context of this picture I was drawing here, so imagine that we just fix our delta V0 to be, let's say, 3. That's not a 3. So imagine we fix things to be 3, and imagine we're working in 3 dimensions. Then we could just insert this operator, what I'm calling delta I Li, with this extra assumption. And then we could have a plot which would then vary this delta I. And in this case, though, in any CFT, we usually assume the spectrum is discrete. There shouldn't be a continuum of operators. And so that means it cannot be the case that any value of delta I is allowed. And so in principle, there will probably be some lower bound and some upper bound. And so then your region generically would probably look some kind of island. But you could only get this island by putting in this extra assumption, which is saying that there are no operators lower than 3 except for this specific operator we have inserted. And so this kind of, like, roughly speaking, is how one gets the best kind of bootstrap bounds, which are islands, both upper and lower bounds. Okay, so this is the one algorithm. Now we can discuss another algorithm.
Shai, I'm not sure if you have actually explained what's special about assuming just everything is above something, some delta, what we call delta LB, as opposed to, let's say, have some intervals of allowed. I mean, what's special about taking, a semi-infinite line and say that the
most general assumption? You could also assume intervals if you want.
No, it's not the most general assumption. It's a very restrictive assumption. But why is this better than the alternative?
You're saying why is it better to assume that just everything above a certain value rather than interval? Well, because we want to be agnostic about the spectrum of CFT data. I mean, we're trying to put in as little as possible.
No, I thought it's because the technical, reason that you need to make sure that this alpha acts on this this the crossing blocks to be positive for all delta in that range, and that's mathematically non-trivial, right? I mean, if you choose some arbitrary subset as opposed to a semi-infinite line, it's going to be technically more difficult.
Well, yeah, sure, it is technically more difficult, but you can also do it. I mean, this is the simplest choice.
So I'm just saying that based on what we have described so far, it's not obvious that it's even feasible to find alpha. That because it's not something. If you look at the condition we wrote, it's not something you can test by a finite number of calculations. Right? Okay,
I'm going to discuss that later in the lecture. Right. Yeah. So right now I'm just writing down the algorithm. I'm not talking about the feasibility. There are many infinities that show up, which we'll have to truncate. That's what I will discuss next. Yeah. So okay. Another question.
Sorry. Could you please explain again the gap assumption?
Oh, yeah. Okay. Good. So let me explain that again. So ask lots of questions. This is kind of the most important. So we have this algorithm, which is that we're saying that alpha acting on these f's is labeled by delta, and L is positive with the assumption that for a given L, all this like delta, for all operators bigger than some bound, where we have like different bounds for every L. So then we said that say we want to bound specifically spin 0, we could just set this delta B to the unitarity bound, which is the default, that's guaranteed, except for spin 0. And for spin 0, we could choose a bound, and then we would have some plot, which would be an upper bound as a function of that bound. But that just gives you nothing. Now I'm saying if we can do more by making an assumption. The assumption is that now we just set our delta B0 to be 3. And so in the context of the original plot, I mean, like probably that would be disallowed because you'd be saying there's no operators below 3. But the way we make that allowed is that we then allow for an extra operator, which is below 3. And so that's what this thing is. This is the extra inserted operator. So the gap assumption is this, and then you put an operator below the gap being 3, which is this delta.
But what rationalizes the number 3? Or I mean, like depending on the problem, how do you choose it? Like,
so this is something we'll discuss later. Yeah. So for now, you just think of it as an arbitrary choice. I'm just saying, for instance, you know, I could have set this to 50, and then I could have inserted.
To do with dimension or anything.
Usually, it will have to do with the space-time dimension, but this is just an example. Yeah, in principle, I could have been 50, and I could have inserted, you know, 30 operators below, and I could have done a plot of 30 parameters. But yeah, I'm just showing you as a simple example. But yeah, good questions, and we'll discuss motivations later. Okay, so now let's talk about another algorithm, which is the only other algorithm we'll discuss, which is the OP coefficient algorithm, i.e. lambda algorithm. And so this algorithm will be similar to the scaling dimension one, but a little bit different. So step 1, we now normalize alpha acting on the F of some specific operator. I'll call, I'll put a star for this. So this is some specific operator, some specific scaling dimension and spin. And so I'm going to normalize this to be S, where S is either plus or minus 1, depending if you want upper or lower bounds on the OP coefficient. So an OP coefficient, say, of the operator star. And then the second step in the algorithm is similar to the step 4, which is that you assume that the scaling dimensions of all, you know, the various spins are all going to be greater than or equal to some lower bound, not counting the identity. And so this does not include, so not including both the identity as well as the specific operator delta star that we're bound. So, but assume this for everything else. And this bound could just be unitarity bound in this case, you know, which is kind of the default guaranteed bound. Thirdly, similar to the other algorithm, we then require that alpha acting on these F's for all delta L is strictly positive or is greater than or equal to 0. And so this is for all L, you know, again, except including these guys. And then the last step is that we will maximize alpha acting on the identity F in order to get either upper and lower bounds, depending on not S is plus 1 or minus. So in the upper bound case, you'll get that this lambda squared by delta L is less than or equal to minus alpha acting on this thing, which is identity guy. And in the lower case, we will get that this OP coefficient is greater than or equal to alpha acting on F identity. Okay, so where did this come from? The idea is that we had our crossing equation here. We act with alpha on this crossing equation. So for everything other than the identity and the operator we care about, that's just positive. And this is why we get, you know, bounds. Specifically for the operator we care about, we normalize its coefficient to be either 1 or minus 1. And then that just means that alpha acting on the identity is then related to alpha acting on the operator we care about times its respective coefficient. And so that's where these bounds come. And so the reason why you get a minus sign here is simply because in one case S was plus 1, in one case S was minus. And so you're going to be maximizing alpha or extremizing alpha. And so in one case, alpha is going to be some negative number, you know, such that alpha will be negative times a negative sign, and then this will be some positive quantity. For this algorithm, alpha will be positive, and then this will also be a positive. But in both cases, the right-hand side will be positive. Although I haven't told you details about alpha, this is just kind of an abstract description so far. So I should tell you a caveat though, which is that while in principle it seems like you get both upper and lower bounds, it turns out that without any assumptions, you will only get upper bounds. Why is that? Because to get lower bounds, you set S to be minus 1. But this step 1, if alpha acting on this equals minus 1, then this is inconsistent with this step. Because this step is for arbitrary operators, But without any assumptions, this delta for these arbitrary operators could become arbitrarily close to this delta star. And so if you want to be able to get an actual lower bound, you have to again make a gap assumption, which is that, let's say we're looking at spin 0, that our delta B is greater than delta star. This is for spin 0. And so this is very similar to the assumption there, because again, you're basically assuming like there's some gap, say up to 3, and then you're inserting an operator below 3, and then you can get both upper and lower bounds on its OP coefficient. But without that further assumption, most generally, you would only be able to get an upper bound on its OP coefficient. And so analogously, if you would want to get some kind of island in terms of the OP coefficient, you would have to make this assumption. Without this assumption, you would only get an upper bound on the OP coefficient. One last comment is that note that in this algorithm, we're actually extremizing alpha. Whereas in the scaling dimension algorithm, we were only asking for the existence of alpha. And so this is why usually the OP coefficient algorithm will require somewhat more delicate numerics, because you're kind of asking more from the algorithm than you are for the scaling dimension.
Shai, I'm not quite understanding your statement of the gap assumption. Are you fixing delta I, or are you letting it vary?
Well, you run the algorithm point by point.
What do you mean by point by point? Do you have a trial value for delta I?
Yes, I have a trial value for delta I, and then if I want to check 5 values of delta I, I have to run the algorithm 5 times. And so like if I were to want to get that island, say I would run it 1,000 times in a grid within that island, and that's how I would get it. That's it. Okay, so any questions about these algorithms before we move on?
But this if you put in the trial value, that would defeat this the rigor of supposedly the rigor of the Bootstrap approach.
Why?
Because you never guess the exact value, let's say, so
no, but I don't understand your objection. I mean, like usually when you're doing the Bootstrap, you're putting in trial values for delta B0, and you're looking at many different values for each different value.
No, I was asking about delta I. What are you taking delta I to be?
Well, delta I is just some trial value below 3 in this specific example. So okay, so it's like, okay, let's go over it again. So without a gap assumption, when you're getting a bound, which looks like this, where this is the allowed region, the way you actually compute this bound is, you look at say 50 values of delta B. For every single value of delta B, you're going to look at say some like grid of points, and you're going to see that okay, these points are disallowed, these points are allowed, and that's what gave you this upper bound. Now, if I want to make this island plot, I'm now going to fix delta B to 3, and then I'm just going to look at again many different values of delta I, and then I'll also see okay, some are allowed, so some are disallowed. But conceptually, it's exactly the same. I mean, like there's no further aside from the gap assumption itself, there's something less rigorous.
Sorry, so far, are you assuming delta I to be the part of the spectrum?
Yes.
So but that was not stated on the board. You're just saying that you're restricting alpha to have this to have an additional constraint on alpha.
Yeah.
But you're actually assuming delta I is part of the spectrum.
No, but that's the exact same thing.
No, it's not the same thing.
So
one is a constraint on the linear function, though, which has nothing to do with what the assumption on the spectrum is.
No, but the only way the Bootstrap knows about the spectrum is from functions. There's nothing else is going on. I mean, like everything that's going on is what's written on the board. There's not something else. Yeah, you have to think about things very kind of formally. Is that like it's not like oh, there's a CFT which exists and then there's this algorithm I'm running out. There's only this algorithm. And so if the algorithm doesn't know anything, then nobody knows. So once I put in this gap and insert this operator, basically I'm looking at a CFT in principle, which said in principle a continuum of operators of any dimension bigger than unitarity, except for spin 0, where it could have any dimension bigger than 3. And it also has the possibility of a single dimension at the specific delta I, which I will then scan over. So that's kind of like the only assumptions about the spectrum I'm making, which the algorithm knows about, and that's fine. I mean, because like this is just a choice.
I'm not understanding why is it you can get stronger bounds by putting more restriction on alpha, because that would seem naively will give a weaker bound. Because you're restricting your allowed.
We're comparing apples to oranges. I mean, there's two different situations. So in this guy, we're doing bounds in terms of this delta B. In this guy, we just fix delta B to 3, and then we're inserting an operator and finding bounds in terms of it. So look, if you were just repeating this exact same bound and then we additionally put in an operator, indeed, the bound would get crappier. But that's not what we're doing. So it's like in this guy, it's like, let's put some numbers here. Like, let's say this would be like 1.5 or something like that. This is what it'll be for the Bootstrap. And so then, your upper bound would say be around 1.5. Now I'm saying, okay, let's fix delta B to 3. So if this had just been 3, it would just clearly be disallowed. But then things get weaker because then in addition to setting this thing to 3, I'm also inserting an operator below 3.
I think the confusion had to do with where does the gap assumption go in your algorithm? Which part of step 1, 2, 3, 4? Where does the gap assumption?
It's step 5. It's an extra thing. So it's an extra thing you add. Okay, so
are you selecting? I'm not understanding at all.
Okay, let me draw a picture, and then I think it will make this clear. Okay, so this is all spin 0 guys. So in print, so originally there's a continuum, which starts at d minus 2 over 2, and it goes to infinity. And so this is what we originally allowed, before putting any assumptions. In the first algorithm, to get an upper bound, we then put an assumption where we were like, okay, we can only have delta B up to infinity. And we can't have anything below delta B. And then we vary delta B. Now, once we have the gap assumption, now we fix this thing to be 3, for instance, and then we add yet another operator, but this operator is only at a specific point, this delta I. So the final spectrum we look at is allowing any operator 3 and higher, and then one specific operator, which is below 3, and then we will scan for the specific delta. And that's how we can get both an upper and lower bound on delta. But
well, my problem is then my problem would be with the scanning procedure, because you're only going to be scanning discrete values.
Exactly. Yeah.
But then it will never be rigorous, because what if the actual theory lies some between?
Sure. I agree. Yes. So look, in principle, you've only looked at specific values of delta I, and who is to say there's not some other delta? Perhaps the physical theory isn't hiding right next to where you look, and that's true. That's why you have to look carefully. So you have to look at many points. But
there are rigorous ways to do this without having to. Well, I mean, of course you can do this numerically, but this kind of result would not be rigorous because.
Okay, but this is how every single paper which is computed islands and Bootstrap has done. This is what they. I mean, it's really like every point you look at is rigorous, but you're saying like maybe instead of actually drawing, this thing, you should have drawn something like, okay, we only checked these specific points, and we didn't actually check it between them. Fine, yeah. So like if you want, you could say like maybe that would be the more correct thing, but in practice you just look at like 1,000 points, and then you're not worried that it's hiding somewhere in between.
I disagree that this is what all the Light and Bootstrap papers are doing. I mean, there are rigorous ways you can establish that there are upper and lower bounds on these. But I thought for that you just need to look at mixed correlators. You're not discussing mixed correlators.
Yeah, mixed correlators is not such a story at all. It's the exact same thing. Okay, these algorithms are completely general. Later in lectures, I will apply some mixed correlators, but nothing about these algorithms will change. Question?
Yeah, maybe to take, I think, a similar question to flip it around. Yeah. I mean, if the actual theory is sitting in between these points, what is the reason to think that this will work? That just because I rule out, some like discrete values that has any bearing on something that could be in between that, right?
Well, yeah, that's a valid point, and this is why you look at many points, and then if you looked at sufficiently many points, you're not worried that like some of the things hiding in between. I mean, look, I should say it another way, which is that like usually your assumption is that you would have some huge allowed region, right? And so you'd be very lucky if you're able to shrink the allowed region to be smaller. And so usually you're not worried about there being allowed regions that are so incredibly tiny that you can't see, because like usually the allowed regions are too big. And so like that's why just in practice not really a concern that there's some tiny allowed region hiding somewhere. Because like you're going to start doing the Bootstrap at some low precision, you're going to have like huge allowed regions, and they'll shrink and get smaller and smaller as precision gets better. And so that's why in practice you don't actually have to worry about some tiny thing hiding out somewhere. But yeah, I just want to emphasize this is nothing with mixed correlators or single correlators. This is just in general how it works. Is that you like to get an island, you put a gap, and then you insert an operator below, and then you're basically just like scanning over different possibilities of that operator. And so you always have the upper bound, but then this will also give you a lower bound.
I don't agree that you always have to choose a trial value. You could also allow this lower operator below delta B to be in some interval. You can set up the program, but that would be rigorous. So that's what I'm saying.
So one could do that. Practice people don't do that, but in principle you could. Yeah. So Yeah, I mean, I guess so. It's important to note that when doing these islands, one should always be careful. There's not something hiding out in between, which indeed is something people always check carefully when making islands. Because you want to make sure that you do a fine enough grid such that you're not finding something like hidden. Because another comment I want to make is that the Bootstrap rigorously says that a point is disallowed. It never rigorously says that a point is allowed. And so it's like the idea is that you're kind of carving out the space of allowed stuff. So you're proving that various points are disallowed, but you don't know if the points you haven't checked, aren't also disallowed. You just don't have enough precision yet, perhaps, to see them.
No, but the point is that if you want to exclude things that are disallowed, the things you are disallowing better not be a zero measure subset, not be a discrete set of points, but for the entire regions.
Yeah, but unfortunately, when you're in islands, in practice, that's what people do.
No, but I think the island can be made rigorous. I thought the intuition doesn't have to do with this. I thought I heard from the mixed correlator is you're turning the picture around, exchanging the vertical horizontal axis, right? Because when you look at the mixed correlator of phi versus some other, I don't know about it's epsilon. If you look at the external operator involving epsilon, it's like turning this picture around, and you would be able to put the restriction on the phi that appears in the epsilon phi OP. Right. So if you rotate this picture by 90 degrees and take the the intersection.
But you don't need mixed correlators to get islands. I mean, you can get an island from a single correlator.
I'm just saying that you can do that rigorously without having to appeal to saying that that you have to do this kind of trial points.
I mean, sure, but I mean, that still wouldn't. Sure, fine. Okay, so I agree that if you are, if your internal operators will be both the x and y axis, then you can rigorously get kind of upper bounds on each. And so I guess you could say indeed you get an upper bound in this direction, say also an upper bound in that direction or something, and then that could turn into that. Fine, I agree. So I should modify by saying that indeed with mixed correlators you can get upper bounds I guess in both directions, and then that would turn it into an island. It's not really, I guess I would say it's not really necessary because you can also just look at a single correlator and you can also get islands. Although I agree perhaps it's somewhat less rigorous because you have to check many points.
Okay, so if you use mixed correlators, the issue of discrete points versus continuum is still there, right?
Okay. So I mean, it depends on the specific context. Yes, I mean, so I didn't want to go into this. I wanted to postpone this to the later lecture, which would be about mixed correlators. But the general statement is that when you're computing an upper bound, you're computing an upper bound on some operator that appears in this OP. And so in this plot, delta phi was the external operator, and delta b was the internal operator. You get an upper bound of delta b. Once you do mixed correlators, which I don't want to go into now, this will be in later lectures, then delta phi could also be an internal operator, and then you could get these kinds of upper bounds, in both this direction and that direction, and then that would then combine to be an island. And in both cases, you would be rigorously excluding everything beyond, a certain assumption you make. But I also just want to emphasize though that that's not really necessary. I mean, perhaps if you want absolute rigor or the continuum of Stanley dimensions, but you can also just look at a single correlator and in principle get an island by doing it again. And in many cases, you will actually get the exact same island. And so you don't necessarily need to do mixed correlators. Yes.
There's no convexity, right, in this delta space?
I don't think so. That's an interesting question. I don't think that's required. I think in many cases it is, but I'm not sure if there's some proof that has to be the case.
Wait, in the plot, you mean?
Yeah.
The plot is certainly not necessarily complex.
Yeah.
I mean, these pictures.
Yeah.
I'm not understanding why you say this gap condition is an extra step. Don't you? I mean, you're just saying that you assume the spectrum to be either above the delta B or it can be delta I. But
Because it's an extra thing you have to put in. So when you're going to put in your list of assumptions on alpha, there'll have to be an extra assumption, which is alpha acting on delta I.
Of course,
Yeah.
but it's in the same step. It's in the same step. I mean,
Sure. That depends on your definition of step. But
okay, but you don't have to run the algorithm to find some bound first and then do this.
Yeah.
That's what I'm saying.
Yeah. But by step, I just meant it's part of the thing to put into the bootstrap. Okay, great. So any further questions?
Is it always clear that there will be only one single unique island, or there could be disjoint sets?
No, so there could certainly be disjoint sets. Yeah. Although in practice, yeah, in fact, even in the simplest case of the Z2 island, indeed, there's an island and then there's an allowed region near the island. You might call it content. So indeed, there would be multiple elements. Any further questions?
Just one question. So the assumption about the gap, which is a very simple assumption that everybody is above something.
Yeah, sure. Yeah.
But I could use some different, more complicated assumptions. In other words, maybe that's more information on the spectrum, which is to say that not everybody is above the same number, but different operators are above different numbers.
Well, okay, you could
So
begin
would that,
Yeah.
so would that, I mean, is it obvious that that would be in the spirit of what would disallow is always disallowed? In other words, something will not come back once you have.
Okay, so you have to just be careful about the way the Bootstrap uses operators, whereas how you might view them from the Lagrangian perspective. So the way the Bootstrap is seeing operators, it's basically looking at them like spin by spin, a continuum of operators. And so like, for instance, you could like put a gap assumption and say all spin 2 operators have dimension bigger than 5, all spin 8 operators have dimension bigger than 9, all spin 0 operators have dimension bigger than 3. You can do that. But within the spin 0 sector, if you want to put multiple assumptions, the only way you can do it is by inserting operators and having a gap. And so if you want, you could put the gap to 5 for spin 0, and then you could insert 2 operators, one on delta I, another one delta I prime. And then you could have some, 3-parameter plot where you're varying delta I and delta I prime, and then allowing a continuum of operators from 5 and up. But that's the only way to kind of tell the Bootstrap what the operators are.
Maybe another way to rephrase this answer is that you could choose other assumptions. Let's say, instead of all the operators are just above delta B, you have some intervals and then something above, some value. But the thing is, if that is very refined, well, you're going to end up, you can exclude that. But you still have many other possibilities left over. So if you want to exclude things, you want to exclude as much as possible. And if you choose the allowed operator configuration to be too refined, then you're not excluding very much.
Making something very special will rule out that very special thing.
Right.
You don't want to make something very special.
Right.
Yeah, but that's a philosophical point.
No, it's not.
Maybe
It's not.
want something special.
For example, this is already a special thing. You assume one operator that's in some very tiny window or at some point right below and then above the gap. That's already assumption. In fact, that's the thing that I didn't like, because it would have been better if you can allow delta I to be in a small interval as opposed to exactly 1 point.
Sure, but that's something we'll discuss in the mixed square loop thing. We talk about islands. Yeah, I mean, I was just trying to say that like there are these general assumptions. And look, this isn't always such a bad thing, because oftentimes you know something about the spectrum. You say you know that there is like a specific operator, some specific dimension below 3, and you want to input. So it's not something to be upset about in general. Any further questions? Great. Okay, so let's
Just one.
Yeah.
So this philosophy of saying, let's put some assumption about the spectrum.
Yeah.
Can it be useful if I want to study, let's say, a CFD with some symmetries, which puts some information on the spectrum, maybe because there are charged or some symmetry, some total symmetry, whatever. And then I will actually be able to justify these assumptions to say.
Well, okay, we're going to talk in a later lecture about bootstrapping when you have global symmetries, because you usually try to put as much in automatic as possible. So most constraints of symmetries will be automatically implemented, so you won't have to put them in by hand, as we will discuss in subsequent lectures. Usually this extra information about specific operators, that's the kind of dynamical information you would have to know, say, from like previous lattice studies or your own genius, or something like that, but like automatic kinematic stuff, will all be automatic. It won't have to do with inserting operators, it's like, that's more about kind of your dynamical information about theory. Okay, so is everyone good with these 2 algorithms? Yeah, so thanks for the clarification. Okay, so now let's talk about how to make this algorithm feasible. Because so far we just discussed some kind of like, in principle, fantastical algorithm, like who knows if you could actually do it. So in order to make this algorithm actually feasible, you have to, you put that on a computer, everything has to be finite, right? Computers can only check finite number of things. And so there's various truncations we have to do in this system in order to make it finite so that we can actually put this on a computer. And so let's list the various infinities we have to take care of. So first of all, there's the spins. Because in principle, when we have this sum, delta L, L is going to infinity. So we can't put infinite, quantities into some computer, we're gonna have to truncate this. The second thing we're gonna have to truncate is delta. Delta is even more infinite than L, because L at least is countably infinite. Whereas delta is some continuum of deltas. It's basically anything above the unitary bound. And so we're also going to somehow have to deal with this infinity. So this thing, you could say is like greater than its unitary bound. And L, you could say right now, in this context, is any even number. at least for the single correlator guy. So this is 1 infinity, this is 2 infinity. The third issue is R, because remember in the definition of blocks, as written in terms of R and eta, we have some sum, of R, say, R going from 0 to infinity. And so currently this block is some, infinitely complicated quantity, at least when written for generic dimensions. So that's something we'll have to deal with. And then the last infinity is the fact that this F itself is a function of U and B, which is a continuously big space of which the functional is acting, because alpha is acting on this F of U and B. And so we can't have infinite dimensional functionals. We have to make these functionals finite. So these are the 4 infinities we have to deal with in order to make this algorithm practical. So let's go through them one by one. So for the first infinity, we do something very silly or very simple, which is we just have a cutoff. So L cutoff. And then we just say that L is going to always be less or equal to this cutoff. So for instance, we will only sum up to say spin 50, for instance. And so I will justify in a moment why that is justified. For now, I'm just telling you what you do.
Well, that doesn't sound very rigorous.
It's not rigorous at all. Yeah.
But in principle, one could imagine doing better. You might be able to prove some linear functional has this positivity for all L, even though in practice that might be hard to do.
Yeah. So for now, I'm just saying you put a cutoff, and so that means you're just putting a subset of constraints. Although I will notice that, like, even looking at a finite number of L, is okay, because it's like you're just saying I'm just going to be putting a finite number of constraints instead of infinite constraints. So I wouldn't say it's not rigorous. It just might not be. It's just not maximum. It's like you're not required to say that alpha acting on every single one of these guys is positive. You're just looking at some subset.
No. If you make this cutoff, you will be essentially assuming you only have operator of that range of spin in your spectrum, because who says that there couldn't be some contribution from operator lies outside of this range that ruins your condition. So then it would not be rigorous, because you're ruling out theories that would never really exist in the first place, because
I'm saying it's rigorous. This is the technical terms. You're not doing a contradiction. It's clearly not maximal. If you're not looking at something physical with the cutoff, unless you can somehow justify that all the operators, if being bigger than the cutoff, somehow barely contribute. But this is something I'll discuss in a moment. So don't worry just yet. For now, I'm just saying what you do. I'll justify it in a moment. Okay.
I'm just saying that if you actually have found a functional that has this property, it might be possible to prove that it actually also holds for arbitrary logic.
Yeah. So that's one thing you could do. Is you could find an alpha which say would have these positivity properties on all L bigger than L cutoff, and then you could then just take your functional and then just act with it on every single other infinite L somehow, and then just somehow prove to yourself that it's positive on all these other L's. So that is something you could do. Okay, so for delta, I'm going to give a more clever method in a moment, but before I give the clever method, let me give a less clever method, which is what people originally did, is that in principle, you could also just put a cutoff on delta and then discretize delta. So say that you only have deltas, in steps of say 0.1, 0.2, 0.3, etc. And then you would have a finite number of deltas up to this cutoff. You would also have to do this for every single L, of course. And so this is what people did originally. Again, people might complain because you could say oh, now I'm assuming, I'm only looking at certain specific deltas, but you could do the same kind of game. You could say okay, I found my functional for a specific set of lambdas and deltas, and then I can just check it for every other value of lambda and delta, and hopefully I'll get lucky and it'll be positive for every other value, and then I'll be okay. And in practice, that's actually what happened. But people develop more rigorous methods, which we'll discuss in a moment. So this is just a stupid possibility. I'll give a smarter one in a moment. For 3, for this expansion in R, again, you just put a cutoff. And so you just expand this thing up to the cutoff. And again, this will be explained in a moment, why that's a reasonable thing to do. And so in particular, and then finally, for this infinite space of U and V's, the way we truncate that is that instead of looking at alpha acting on F for any U and V, we're just going to look at derivatives of U and V expanded around what's called the crossing symmetric point. And so in particular, let's rewrite our expression for the sum over X now that we've implemented some of these truncations. So first of all, we're looking at L next to our L cutoff, less or equal. We have our OP coefficients. And then we have derivatives in terms of Z and Z bar. I'll remind you what those are in a moment. So now this has an extra label, R cutoff. Okay, so what's going on here? So first of all, we are now just looking at derivatives in terms of z and z bar, where I'll remind you that u equals z times z bar, and v equals 1 minus z and 1 minus z bar. So these are just different coordinates. And the reason why it's useful to look at this point is that this point is invariant under the crossing where u goes to v, which remember was our crossing equation, which is how we define these steps. So that's one reason why it means to look at this specific value. In terms of the r and eta coordinates, so eta c is 1, and rc, which is just z bar equals a half, this ends up being 3 minus 2 root 2, which is approximately 0.17, which is a small number. And the fact that this is small will be important in a moment. Okay, so that's how we truncate this guy, is that we're just looking at certain derivatives. And so now the vector space, instead of being infinite, which what it would be for general u and v, it's now parameterized by a certain lambda, where say that we look at derivatives of, for instance, m plus n lesser or equal to this lambda. And so there's some other details where it's like only certain derivatives are even non-zero. You know, in this context, you can only look at odd derivatives. And so the point is that this thing is now finite. And so the precise finite number is given in my lecture notes. It's not so important, but obviously it grows with lambda. The other thing is that once we have put this R cutoff on the blocks, so remember the full block formula was also involving, you know, sums over delta, you know, minus certain specific poles. And so if we're only summing R up to a certain value, that means we're also only going to be including a finite number of these poles. And so this will be important in a later step, which is where I will show how you can reformulate this thing as a polynomial in delta. But before I do that, I first just want to convince you that there's a reason why you were justified in putting this cutoff on spin, and there's a reason in principle why you'd be justified in putting a cutoff on delta, and why also it's reasonable to expand around this point with R equals 0.17. And so let me do that, and then afterwards I will show you a better method of how to take into account this, you know, looking at all continuums of delta bigger than unitary. Okay, so just bear with me for a moment. And so what I'm going to do in order to show that at least the cutoff on spin and a possible cutoff on delta is rigorous, because that's how people originally did Bootstrap, is I'm going to review this proof to the Slaughter-Hitchcock and others that this sum, that the tail of the sum is small in a way that's related to R that you can quantify. And so basically I'm going to convince you that operators of really high dimension and really high spin contribute in a precisely understood way, which is extremely small. And that's why it's kosher to ignore it. Okay, so let me just kind of review this proof very briefly. I won't show all the details, but I do think it's important to understand how this proof works, because it kind of conceptually justifies a lot of what's going on. So basically, you start off by recalling that, you know, from the previous lecture, that when R is very small, the block, an individual block, goes roughly like R to the delta. So that's the statement we start off with. And so the next thing is that the block is also a function of eta. This function of eta is written in terms of something called Gegenbauer polynomials, and their maximal value is in eta equals 1. So if we want to get some bound on blocks, in particular sums of blocks, you know, without loss of generality, we can just set eta equals to 1, and the bound we get will certainly apply to more general data. So that's just another way of saying that G delta L of R eta is always going to be less than or equal to G delta L of R1. So let's just deal with eta equals 1, then for simplicity. And so in practice, when eta equals 1, that means we're looking at a 4-point function on the line. So we're looking at so the first scalar, the first identical scalar we put in R. The next one we're looking at minus R. The next one is at 1, and then the next one is at minus 1. So we put these operators on a line in this specific configuration. And so in particular, this is GR1 divided by 2 to the 4 delta phi, where I'm defining this auxiliary quantity G here as sum of blocks. Where this prefactor just comes from the usual, 1 over x1, 2, 1 over x3, 4 to various values of delta phi, which we have in the 4-point. So for the purpose of this proof, it's convenient to write this G of R1 as a some coefficient delta B delta time introducing times R to the delta. So another way of saying it is that let's just think, this thing is only a function of R, and in particular, it's going to be some infinite polynomial of R. So let's just write it as an infinite polynomial as such. So it's polynomial of R with powers of R labeled by this delta, which follows from the recursion relation expressed into the block, and we'll go into with various coefficients B, which are then just numbers. And in particular, you can convince yourself in the recursion relation that these B's are always positive. Okay. So then, as long as unitary down is set. So then we have that the sum for over delta for all delta bigger than certain delta star of the block expansion, which is the OP coefficients times these blocks. So this is the thing we're trying to bound, right? Because we're trying to say that like all blocks times OP coefficients of scaling dimension bigger than some delta star are small. That's what we're trying to convince you. We're trying to show that the tail of this sum is small. And so, so based on these definitions I've shown you above, so when we're setting 8 equals to 1, this thing is always smaller than B delta R to the delta, where delta is greater than or equal to delta star. And the reason why this is true is that the right-hand side contains all the terms of the left-hand side, as well as additional contributions of descendants whose little delta would be bigger than delta star, that come from primaries of delta less than or equal to delta star. So if we want to bound the right-hand side, we should then consider the limit of R goes to 1 in this 4-point function. So let's furthermore consider the limit where R is going to 1, in which case you could show based on the explicit expressions that this thing is roughly 1 over 1 minus R to the 4 delta phi. And so then this implies, just comparing to the definition here, that in this limit, P of R1, this is when R is going to 1, is going to look like 2 to the 4 delta phi over 1 minus R to the 4 delta in this specific. So another way of seeing why this is the case is that you can just take this 4-point function and in this limit, you just factorize it to 2-point function. Each 2-point function looks like a square root of this, and then you have 2. Okay, so now we want to match the asymptotic of this G of R1 by assuming power law growth for the coefficients. By coefficients, I mean these B's. And so let's assume that when the delta of these B's is very large, then they're going to have this power law growth. In a moment, you'll see why I'm assuming this power law growth, but for now, let's just take this as an assumption. So with certain convenient coefficient. And then you can approximate this sum over these B's, which I wrote here as an integral. So we approximate the sum as an integral, and then we do the integral, where we assume the B's look like this, and so you just do this integral over R, or the integral over delta, and this will give you 2 to the 4 delta phi over 1 minus R to the 4 delta phi. And so now you see why it was reasonable to assume this kind of polynomial growth, because this reproduces, the expected answer when R is going to 1. And so that justifies this kind of ansatz for this growth. And so then this means that the sum over these coefficients B delta can then be approximated. So let's introduce this auxiliary quantity I of E. And so we just define this as the sum of all B's, where delta is bigger than E. So this is a function of capital E. And so this thing, again, we approximate the sum as an integral over delta. So just putting in the definitions, you have 2 delta, the 4 delta phi over gamma of 4 delta phi. And then you just do this integral and you get 2 e to the 4 delta phi for gamma of 4 delta phi plus 1. So we kind of assumed this polynomial growth of B delta, and we've also been replacing sums by integrals. And so this might make you guys nervous because you might think like, oh, how are all these steps justified? Maybe you're pulling this out of our ass. And so I would just making these assumptions for simplicity, but you can also prove these things rigorously from something called Hardy-Littlewood-Tauberian theorems. And so whatever those are, they show that those steps are rigorous. But for now, let's just assume this is a reasonable guess, because after all, it did reproduce the R goes to 1 value. And we're just going to use this fact in a moment, which is that this I of E, which is summing all B's up to E, is roughly this, E to this power of 4 delta phi times this factor. And so now we're going to use that to show our final group, which is what we'll do next. You must see. Let's go with it. Okay, so hopefully you can see this. So delta bigger than delta star, the delta R to the delta. So this is the thing we're trying to find, right? This is the tail of the sum of OP coefficients times flaws. So even if you guys are following all the steps, make sure you understand. Does everybody know what this quantity is? This quantity is supposed to be the tail of the sums of OP coefficients times flaws for very large values of delta. And so we're trying to bound that tail. So this guy, yeah.
And this includes all spins.
Yes, all spins. Yes, yeah. Because the spins are related to delta by unitarity. So they're kind of dragged along, with delta. So this thing, by definition, I don't know if everybody was following all these definitions, but just believe me, according to the definitions that are above, just unpacking them, this is an integral over E of these things I defined as VE. And then there was a sum of all deltas less or equal to E of delta function R to the E. And so then this thing, we can just integrate by parts, and we get minus log R, and then there's an integral delta star dE 1 of I of E minus I of delta star R to the E. Then this thing is less than or equal to minus log R integral dE I of E. And then this thing itself, you can approximate by minus log R E 2E to the 4 delta phi over gamma 4 delta phi plus 1. So this is just putting in these factors. This was kind of like assuming the way this function of thing depends on E, which can also be justified by these Tauberian theorems. And then this final thing is less than or equal than just a 2 delta star to the 4 delta phi over gamma of 4 delta phi plus 1 R to the delta star. Okay, so this is the important point, which is that this tail here is bounded by R to the delta star, where delta star is some big value of delta. And so this means that if we're expanding R around some small value, which we are, because when we expand around this cross-symmetric point, R is roughly 0.17. This means that operators with very large delta are going to be like 0.17 is a huge value, and that's extremely small. And so this is getting smaller kind of exponentially. And so this is why, in practice, it's reasonable to neglect very large values of spin, or alternatively, very large values of delta, because they contribute exponentially small to this sum. And so this is a very important kind of conceptual justification of some of the truncations we do. But even if you didn't follow all the steps, the important thing is just to get the last thing. Okay, so let me go back to this infinity in terms of delta. So I said that one thing you could do, which what people originally did, is just to discretize delta and then look up to some delta cutoff, and that's justified, by the fact that this tail is very small. But there's actually something better you can do, which was developed by David Sutton, David Poland, Philip Coase, and other people, which was basically to rewrite these blocks as polynomials in delta, and then impose positivity of a polynomial of delta. And that's the more modern approach. So that's what we're going to discuss in the remainder of this lecture, and then I'll give a demonstration. So in particular, the way you do that is that if you've already truncated the sum up to some R cut, so that means you've written this as some meromorphic function of deltas. And so what you do is that you just multiply in this expression, you multiply the whole thing by a positive quantity, which is going to be, let's call it chi. And this chi is just a function of delta. And this thing is basically going to just be a product of a bunch of poles. And so, and then you also divide by R cutoff to the 4 delta. And so if you multiply this expression by this positive quantity, where it's important that this thing is positive for all delta, then it's going to kill all the poles in each individual block. So this is the sum of all poles in all blocks up to this cutoff. And then it's also going to kill this exponential for R to the 4 delta factor, such that this quantity will then be a polynomial in delta. And it's okay to do that because the only thing you're requiring is positivity of these OP coefficients. So rescaling the OP coefficients by this chi of delta is okay. That's still positive. And so then at the end of the day, you now have the statement that a bunch of polynomials in delta, finite number of them, have to be positive. And that is the thing which you can then implement using semi-definite programming, which is what we're going to discuss next. Okay, so let's discuss that now. Okay, so let's kind of review what we have so far. So we have a list of polynomial constraints where now we can label this alpha by variables m and n, which is corresponding to each derivative. So there's a finite number of them. It's no longer simply cubed infinite space. We have some polynomials p, which are basically derivatives of this f, and then multiplying by the chi so that they become polynomials in delta, as I just mentioned. They're also a function of delta phi. This thing has to be greater than or equal to 0. For some fact, which is delta bigger than delta b. And this is going to be for all even space, as discussed before. Then we're going to have some kind of normalization constraint. So this is I'm just writing down what we got from the algorithms, but now writing it down after having done these various truncations. And so the normalization constraint so this would be, depending whatever normalization value you're using. So this thing is normalized to 1. And then there's going to be a certain quantity, let's just call it OMN, that alpha is max, that alpha is extra max. And so this basically describes both of the algorithms we discussed before. And so how do we actually implement these algorithms? It's a polynomial, this is a normalization, and there's a quantity where extra. And so the way we do it is that you can consider what's called a polynomial matrix program, is where we consider a set of mj by mj polynomials, symmetric polynomials in particular. And so let's just define this with these two labels, w and j, as a polynomial x. And this thing is just going to be a bunch of polynomials labeled by w and j, and then with a bunch of entries. And then we would fill up this matrix as follows. So in terms of this matrix of polynomials, so it has labels where w is less than or equal to some capital W, and little j is less than or equal to capital J. And so then the goal of a polynomial matrix program, it's called a PMP, is you want to maximize E0 plus a sum for all y, which is a certain vector in W, such that M0j of x plus sum such that this thing is positive semi-definite for all x greater than or equal to 0, and where we label these things by this j. So this is the definition of our PMP, and let's compare how this matches to our abstract algorithm. And so these y's correspond to the functional alpha. So these y's as labeled by W, these correspond to the alphas as labeled by M and N, except this is after imposing the normalization. So it's going to be kind of like one fewer y than there'd be alpha, because one of these alphas is eliminated by this normalization step. Also, for this single correlator algorithm, we can just specify to MJ being that. So instead of having a matrix of polynomials, we can just think of this as just one polynomial. So let's just think of M as just a single polynomial. The matrix of polynomials is something we will consider when doing mixed correlators. But for the simple single correlator case, we should have one polynomial. And then in that case, this matrix M of X is just exactly this quantity P of delta, where delta is X. And so then the fact that X is always greater than or equal to 0 is then equivalent to the fact that delta is greater than or equal to unitary X, for instance, or more generally to some delta B. And so X is just some shifted delta in this algorithm. And then this constraint is that this thing is positive, is just this guy is then exactly this guy, because M is just this P, Y is just this alpha. This M0 is something you got just by imposing the normalization condition. So that's why I put up this constant guy. And you're basically just saying that this thing is strictly positive. And then the quantity you're maximizing, that's what this OMN is. And remember, for the scaling dimension algorithm, you're just maximizing 0 because you're not maximizing anything. Whereas for the OB coefficient algorithm, this OMN would be, the F for that specific operator we're maximizing. And so that's how you map our abstract bootstrap algorithm to a PMP. And so then the next thing we do is we then rewrite this PMP in terms of what's called an SDP, semi-definite program. And so basically the statement is that you can take any polynomial of X and you can write that as a matrix which is constant X using some basis of symmetric polynomials. So I won't go into details into that basis, but the claim is that there's some basis. Let's label it I with various labels. And this basis allows you to turn some polynomial of X into a matrix, call it Y, which is no longer a function of X. And you use that, and you do that by using this basis symmetric polynomials. And in fact, you can even do this for matrices of polynomials, which will be useful in later lectures, but for now, this is just a single polynomial. And so then the statement of an SDP is, so there's two versions of the SDP. The first one's called dual. And in the dual version, you maximize, so this is the same B as before, the same W as before. So you maximize these Bs with the Y's. Remember, Y is basically our functional for all Y, which is a certain vectors, as well as this matrix Y, such that so this is just some constant guy. I'll explain what these labels mean in a moment. Plus so this A, remember, is the matrix which allows you to go from a polynomial to a constant matrix Y. And Y is then itself semi-positive, semi-definite as a matrix. So Y is a matrix. K is certain values where, like, the way you go from this polynomial to this matrix is that you evaluate this thing at certain values K. And this is what allows you to write a matrix in terms of a polynomial. And so this is what the dual problem is. And the rank of the matrix Y is related to this rank of the alpha, which was related to basically the size of the original polynomial P, which is written in notes, but I won't go into it. There's also a primal version of this algorithm, which is basically the dual of the dual, as people call it. So it's kind of funny language because the dual is really the main thing we care about, and the primal we care about a little bit.
Shai, maybe there's some typo in the last equation. The right-hand side X is supposed to be XK. You're evaluating on these discrete points XK.
Yeah, this should be XK. Sorry. Yeah, I got K there. Yeah. So it's evaluated discrete points. These discrete points is what allowed us to write this polynomial in terms of this constant. Thanks for pointing out the typo. And the primal version of this is that we minimize. So again, this is the same B. Now we're going to sum over J, R, S, A, which is the various labels, the constant part of this matrix, these XKs, and then we introduce this dual Y. So it's like the dual of the functional, RXK, where this dual is now in the dual space, RP. They're going to define some dual matrix Y, which is defined as JRSK. Well, it's not defined, but it's like written, where you have this matrix A from before, JRS, evaluated with points XK, and then contracted with your dual functional Y, KRSK. And so then you minimize this quantity such that JRSK of your constraints, JRS XK, Y tilde, JRSK equals minus B. And you demand that this Y tilde also be positive semi. So this is the dual version of this primal problem.
How many points XK do you have to take, or how do you choose them?
So there's a canonical way of choosing it when going from when using this base of symmetric matrices to go up the polynomial to Y. The precise number of points K, it's written in my lecture notes. It's kind of ugly form, so I don't want to go into it at the moment because we're a little short on time. But it's a finite number of points. Which
But it's determined by the degree of the polynomial?
Yeah, it depends on the degree of the polynomial. Yeah, it's going to grow with the degree.
Nothing else?
Yeah.
Right.
Yeah, it grows with the degree of the polynomial. Also, if you have a matrix of polynomials, it will grow with obviously the range of the matrix. So now we have this dual and primal program for our STP, and then there's a program called STPB, which was developed by David Stucken, which then solves this primal and dual problem simultaneously. And so you start off with a guess for these four values. So Y0. So if I'm running by 0, I mean your initial value. So you have your Y, which is a vector. You have your matrix capital Y, which is a vector. You have the dual Y, and then you have the dual matrix Y. So these are kind of our four, variables in these things. Because everything else is fixed. B, P are just fixed, for the specific problem. Like these are, practice derivatives of F's. Y is a functional, and this capital Y, is related to the polynomial constraints. And so you start with a guess for one of these guys, and then starting from that guess, you kind of move in the space of these Y's, you take something called the Newton method, in order to basically satisfy these constraints in the dual and primal problem to the greatest extent you can. And so, for instance, you can define these deltas, which are going to be deviations from the constraints in these problems. So in the primal problem, we have two definitions. One of them is that, the sum over this P, I'm just being very sketchy here, times Y tilde plus B, that this thing is supposed to be 0, right? Because that's the definition we wrote right here. And so we want this thing to be approximately true. And so this measures how close we are to this being true. We can then define a second primal deviation, which is just saying that this thing has to be true. And so in this case, this Y tilde minus the sum of A, Y tilde, that this guy has to be true. And then there's a third deviation, which is making sure that this thing is true in the dual problem. So this guy, we call the dual, I'm not writing all the labels, is P0 plus a sum over W, YW, PW, minus trace A1. And so at each step, basically the algorithm is trying to minimize these deltas so that the definitions in these programs can be satisfied. At the same time, it's also trying to extremize. So the program is also trying to extremize the objective functions, which are these. So it's trying to extremize this, and it's trying to extremize this. So it's doing two things: extremizing these two quantities, and it's also trying to satisfy the definitions in the dual and primal problem, of which there are 3. And so the program tries to do that. And so when these deltas become smaller than a certain threshold value, which you, the user, can input, called, say, the primal error or the dual error. So when these guys are smaller than something called the primal error, then you say it's primal feasible. So if this is smaller than a certain PE, then we say it's primal feasible. And if this thing is smaller than a certain dual error threshold, which you can specify, then you say that it is dual feasible. Once it's both primal and dual feasible, i.e. once it's approximately satisfying the definition of this dual and primal program, then it proceeds to extremize the objective functions. So at that point, so let me just do a short computation. So this P0 of xk times y tilde minus bwyw. So this thing, after you unpack all the various definitions, is approximately the trace of y tilde y, after the problem is primal and dual feasible, which is strictly possible. So basically, once you are approximately satisfying these properties, then just using these definitions, you can rewrite this quantity as something which is then strictly positive, and then you try to get it to be as zero as possible. And this quantity is just the thing you're trying to extremize. And so once this quantity becomes small enough, i.e. less than some duality gap threshold is what you call it, then you say that the SDB program has terminated and it's possible. And so in practice, so applying this formalism to the two programs we discussed, scaling dimension upper bounds as well as OP coefficient upper bounds. For scaling dimension upper bounds, all we're trying to do is see if an alpha exists at all. So in that case, we just want to see if it's primal feasible or dual feasible, because we just want to see like if there is enough. It's only for the OP coefficient algorithm that we further are actually trying to extremize some specific quantity. And so in that case, our goal is then to actually get the optimal solution, which is not only is it both primal and dual feasible, but furthermore, you then try to extremize this quantity as much as possible, where this quantity translates into the bound on the OP. And so that's how the two SDBs relate to our programs. So in the remaining, I guess, 50 minutes, because we started late, let me demonstrate how this works in practice. So thanks everybody for dealing with the technical limitations. Okay, so let me lower this thing. I guess it already is lowered, right?
Yeah.
Great. Okay, so everybody can already see it. Okay, so let me demonstrate what's going on in a few steps. There's a certain wrapper file called bootstrap.m. This wrapper file I put on the Slack, and also it's available from the source file of the lecture notes, which people have also been looking at. And so let me kind of just briefly show you what's going on in this wrapper file. So at the top of the file, there's a list of parameters you put into SDBB. And so you should recognize some of these parameters that I just described. So for instance, there's the duality gap threshold, which says like how close you are to optimality. There's the primal error threshold, which says how close you are to declaring that the program is primal dual, or primal feasible or dual feasible. Then there's various other parameters that you can kind of leave them what they are. They never, for most cases, don't need to change. The only other important guys is you have these conditions where basically these conditions tell the program just to stop the moment it becomes primal or dual feasible. And so these conditions you turn on when applying the program to the scaling dimension algorithm, because all you care about is whether or not the alpha exists. You turn them off when trying to extremize a quantity, which is what you do for the OP coefficient algorithm. So in that case, you set them to zero. So that's what's going on with these parameters. Then there's a bunch of crap you don't need to worry about. This is just stuff which is converting your input into some format which SDBB likes. So this you can all kind of ignore. But then now let's get to the interesting part. So this is an example of a wrapper function, which will produce input, say for the simplest bootstrap one we've been discussing so far, which is the 4-point function of 4 identical scales. So that's why I called it icing, because it actually applies to the icing model. And so what goes on in this wrapper file? So here, this is where you define your f's, which are the f's we've been talking about, which is derivatives of z and z bar of the block minus its crossed version, evaluated for a bunch of derivatives. And so these derivatives, you can either compute them by hand, as we discussed in previous lecture, but I will also show you there's a code on Docker, which is also available online, which just computes derivatives of these blocks for you. You don't actually have to do it. Although for your own understanding, it's good to do it at least a couple times. So that's what this F does. This CD polls is just telling you what polls are included when you've computed an F with a certain R cutoff. Because remember, a finite number of polls were included. This is polls in terms of delta. And so then this is where we input the constraints of alpha acting on the F's, for the various spins. So here, for instance, we will have a table of all spins up to a certain spin cutoff.
And then we just put a, an F where we're only including odd derivatives, the derivatives are 0. Here, we're just saying what the value of delta phi is. And then there's some subtlety where, you divide by X for spin 0, just it makes the thing a little bit more numerically stable. And so these are the constraints of derivatives acting on F for general operators of general spin. If we want to insert an operator, I also include some code which does that. And that's basically just the extra derivative of F with alpha acting on it. That's what we call delta I. And then there's the quantity we are extremizing, which for the scaling dimension algorithm is basically just a bunch of zeros. And so that's trivial. And finally, you input that into a function called write bootstrap STP. So here you're putting in the quantity you're extremizing, which is just a bunch of zeros, the quantity you're normalizing, which is just the unit operator, and then the other constraints. And so this wrapper file is fairly simple. I mean, it's just a few lines of code. I think each line is fairly self-explanatory. And so the idea is that once you understand this, you can then generalize it to say other problems you want to consider. Similarly, there's another wrapper code, which is for extremizing OP coefficients. So I call this icing CT. The reason I call it icing CT is, remember from previous lectures that CT, which is the coefficient of the stress tensor 2-point function, if we unit normalize this, then CT is proportional to 1 over the OP coefficient of the stress tensor squared. And so by doing an upper bound on the stress tensor OP coefficient, it's a lower bound on CT. And that's a quantity people care about. So this code is extremizing OP coefficient. So most of the code is exactly the same because the constraints are still the derivatives of X. The only difference now is the quantity you're extremizing is now specifically the stress tensor. So here we input derivatives of F specifically for spin 2. We multiply by some normalization factors such that CT will just be literally 1 over the thing we're extremizing. And then the quantity we're then going to be, since we're normalizing, the quantity we're extremizing is then the unit operator. And so that's what these wrapper files do. And so let's just run these wrapper files just to produce the input I just described. So here I'm just going to run the file. Okay. So the first thing we need to do is we first need to compute blocks. So I'm just trying to show you every possible step. So the first thing we do is we go to our terminal. We'll speak about 5 minutes.
We have a class.
We have 5 minutes.
Yeah, it's 11:45.
Okay. Okay. Yeah. So what we got to do? Okay. So you compute these blocks using scalar blocks. After computing all these blocks, then you can run the wrapper file like so. And then you can then run, so the code runs in 2 steps. So the first step is you have to convert the stuff using something called PVM to STP. And so we're going to do that for 2 input files. Okay, well, let me just show you what happens because I guess we have a couple minutes left. So basically, you first run this PVM to STP where the commands are written in the lecture notes, they're also written here. And then what's going to happen is that then afterwards you run STPP, and let's show what happens in each case. So when you're computing scaling dimension bounds, if you're looking at a point which is supposed to be disallowed, then you're going to find the code's going to run, and the primal objective value and dual objective value both become very small. This means you found an alpha, and if you found a functional, that means there's a contradiction. That means that point is disallowed. If the point is not allowed, then it only takes a few steps because basically it's not going to find a solution. And so that means primal objectives are going to go to infinity, and and then you're set. For the OP coefficient algorithm, so now you actually want to find an optimal solution. So then the code's going to run, primal objective and dual objective are going to get smaller and smaller and smaller until they become basically, the actual value, which in this case is minus 1.06. So this is your bound. Well, minus that is your bound on the OP coefficient. And so if this OP coefficient is then greater than or equal to 1.06, that means CT is going to be, basically less than or equal to something like 0.95. And that's actually what's expected, because in a good normalization, this is the value. And so just to show you some quick plots of what the results would look like. So if you run these algorithms for many different values of delta phi, what I call it sigma here, delta epsilon is just the spin 0 scaling dimension, you can basically carve out this plot. And then similarly, you can also run the OP coefficient or CT, and you can get this plot. And as you see, this red dot is Monte Carlo value. You will find a kink right near the Monte Carlo value for the icing model. Similarly, you find a minimum for CT near its expected value. And so this is something you guys can actually do just by following what I demonstrated in today's class, using the Docker code, which I shared with everybody, as well as the wrapper code, which is also shared. And so one final comment is that there's gonna be a month-long break in this class. And then when we reconvene in a month and a half, hopefully you guys will have some experience running SCBB. You can email me with questions in the interim. And then we're gonna talk about more advanced methods, such as introducing global symmetries, doing mixed correlators in order to get islands, and also like the future of groups. Okay, great. So I think that's it. So maybe you can ask questions as we file out, so this angry man doesn't attack us.
So I think